So welcome to this Datadog On episode. Today we're going to talk about cloud workload identities in a multi-account, multi-cloud environment. And my name is Christophe Tafani de Reper. I'm part of the security advocacy team at Datadog, working on open source and cloud security topics. And today I'm joined by two great people. So we have Tabitha Sable and we have Ian Ferguson, whom I will let introduce themselves.
Hi, my name is Ian. I'm a staff engineer within our infrastructure group, within Datadog in our engineering group. We have a lot of teams that work on building the product and improving it. And the infrastructure group is responsible for building the platforms and services that all of our engineers who build the product build and deploy and operate the products on top of. And part of that responsibility includes helping our engineers interact from our platforms and environments with the cloud providers that we depend on.
Hello. Like it says here, I'm Tabitha Sable. I'm a staff engineer in the security organization here at Datadog. I like to joke that my job is to stick my nose in everybody else's business very carefully so that they want to thank me for it. Because really what that means is that I get the opportunity to work together with folks all across Datadog engineering when they have challenges in their application development or maintenance lifecycle that have interesting security properties in them. And so I get to hack things, make friends, and hack things with my friends on diverse topics from vulnerability management to things like brokering cloud provider IAM access.
Thanks a lot for the great intro. And so now we're going to get into the meat of it. For everyone who is still joining, welcome. And we are going to have a Q&A section at the end. So feel free to ask any questions. There's a chat as well. The goal is to make it a bit interactive as well. So we'll have a bit of time with Ian and with Tabitha at first, where they will show us what they did internally at Datadog. And then we will move on to the Q&A and the discussion part. So Ian and Tabitha, the floor is yours.
So yeah, sort of as I was mentioning, security work is interesting to me, in part because of the interaction between people and processes and technologies, and in a really more abstract sense, the fact that there is the difference between the ideal, the thing that you think about or the thing that you think you know, and the real, the thing that really exists in the world. And so the advantages of running on just one cloud provider are pretty widely understood, and they have to do with that discrepancy between the ideal and the real. We can think about the properties of that cloud provider's products and services in the ideal world that's like described by its documentation. And when we find that there are discrepancies there, when we have problems that arise in the real world because it doesn't match the way we think about it, we can file a bug. We can complain to the cloud provider. We can ask them to change it or improve it, or at the very least to update the documentation so that way it matches our understanding a little better. And that kind of simplicity is a really powerful element of the argument in favor of running on a single cloud. It is what it is, and if you don't like it, you can complain. You might be able to change it. But somehow or another, many of us, I might even guess most of us, once we are working in an environment past a certain size, find that we have workloads in multiple cloud providers. Maybe a merger or an acquisition brings another pre-established cloud presence into our lives that we weren't expecting. Or maybe as the company grows, certain customers don't want to do business with certain companies that are big cloud providers, and so therefore they ask during the sales process, like, are you running on AWS? Are you running on GCP? We want to make sure that, that our money isn't going to, insert whichever cloud provider a certain customer might not like. Or maybe as you grow your cloud presence, the worry about being locked into that cloud provider and the shared fate problem starts to be a concern for your leadership. And so they ask, what would it take to have vendor diversity in our cloud environment? Or maybe you're still migrating workloads to the cloud, or maybe you have applications that you are repatriating to on-prem from the cloud because of whatever reasons, certain kinds of cost savings or certain kinds of data governance problems. And in a hybrid environment like that, you get many of the multi-cloud challenges, even if you're only on one cloud. So since we are now having more than one cloud provider, we have a lot of new engineering challenges. To provide a consistent experience, you need to build your own platforms that your users can reason about. And you can only build that on top of the common area between the cloud providers that you're running on. So you miss out on a lot of the best stuff, or alternately, you expose the complexity of all three cloud providers to all of your users. And in either case, you end up having to deal with this question of what is real a lot more. And so that's sort of where this talk starts. As Datadog has grown and evolved and, moved on to additional cloud providers, we have gone through several different stages in how we address our multi-cloud challenges. And hopefully, by sharing some of those experiences, we can help you to get there with less pain than we had. Slide.
So one of the things that we found at Datadog through that evolution that Tabitha described is that there's a lot of intersection between those security needs, but also making systems that are usable by all of our engineers, as well as making systems that are reliable to host all our products. All three of those things, to make them work, to have secure, reliable, and easy use systems that span tens of thousands of hosts and thousands of engineers across multiple cloud providers in multiple regions, all of that requires us sort of doing some amount of abstraction and a heavy amount of automation. At the end of the day, a lot of times if an engineer is working on a product that maybe needs to store data, they just want to have a nice, safe object storage interface in front of them, and they want to put stuff in the object storage bucket and maybe don't want to have to care about which cloud provider is it in, or within one cloud provider, maybe which Azure subscription is this particular blob storage thing in. And that's, again, just as true. That's a user experience thing. But also on the security side, like if we know, if we sort of automate which services based on their identities and things can access which accounts or which resources and how we link our internal Kubernetes platforms that we rely on heavily to those resources in an automated way, users don't have to remember like, oh, I mapped, this service called Rocky to this account called Bullwinkle. It's just always the same. It's just if they're thinking about a service called Rocky, it's just always going to be mapped to an account, an identity named Rocky. Similarly, very good for reliability. One of the things we saw, and we'll talk about, or Tabitha will talk about in a second, is like in the past, we often had shared service accounts between multiple applications because it was easy for engineers to get going. We weren't automating things for them. And somebody on one of the services would modify permissions or change the account and it would break things for the other service. So it's not, the security best practice of don't share identities between discrete things, pretty well known, but it bit us on the reliability front as well. So one of the ways we approached this engineering was sort of as we went through some of the evolutions that Tabitha is about to talk about, was thinking, how do we solve these by internalizing the complexity of the underlying environment and presenting users with interfaces that let them care about the things they want to care about and not care about the underlying details that we know more about and that we don't want them to have to care about.
We're going to tell a story. Let's go back far into the mists of history before Kubernetes, when developers were writing their applications and then running them in what I like to think of as a classical DevOps environment. So each team at Datadog owns and maintains their part of the application through its whole life cycle, prototyping, development, maintenance, and eventually replacement with something else when there's a need to improve it. And so in this sort of classical DevOps environment, teams had access to cloud provider resources, cloud provider APIs. They would write Terraform to define the auto-scaling groups and load balancers and storage buckets and things like that they needed. And then once those resources were running, they could maintain their virtual machines with Chef, like very very typical sort of classical DevOps environment. And as we migrated out of that sort of classical DevOps environment into running on Kubernetes, we had to give up the immediate IAM niceties that users got from running their code directly on cloud provider VMs. So within a cloud provider, there's automatic identity provided by the cloud provider's API and makes it easy to assign certain roles to a VM, and then you assign applications to that VM via Chef, and there you go. So as we migrated into Kubernetes, we had to give up some of those nice things. Slide. And so had to patch something in there in order to make up for that. And Kube to IAM is a, at least formerly well-known open source project, which helps to bridge that gap in a AWS specific way. And so in the first AWS hosted Kubernetes clusters that we had, we ran Kube to IAM for AWS access. But then when things needed to access GCP resources, we didn't have something like that. And so we had to generate static keys and store them into KV storage, like we stored them in Vault. There are other places that you could store them. And so this worked. This got the users to be able to migrate their applications off of the Chef managed VMs and into Kubernetes. But there was a bit of extra complexity and a bit of a loss of functionality there. So, unfortunately, with Kube to IAM only working within AWS, that didn't help us in any of the occasional cases where there was a cross-cloud access that needed to be made. And there's an interesting security boundary degradation too, because Kube to IAM runs as a daemon set, which is a pod that gets automatically spun up on every node within a cluster. And so that means that a particular Kube to IAM pod would have access to any of the AWS roles that would be needed by any pod that landed on that node. And so there is an interesting possibility there by accident or malice of landing new pods onto a node that you already have access to in order to increase the permissions that are available to Kube to IAM, and you go and do your nefarious things. And these are the sorts of problems that you address with patching, you address with migrating nodes from cluster to cluster, migrating workloads from cluster to keep them apart when they're very important, but it's a difficulty. And so then on the GCP side, there's an additional difficulty with those static service keys. A person has to generate them, has to store them into Vault, has to rotate them manually. And so there was a reduction in security properties, there was a reduction in convenience, and there was an increase in the amount of just ongoing keeping the lights on work. So, slide. This was bad for usability and security and reliability. It got the applications running, but it wasn't ideal. So in both cases, you ended up with different services being able to share the same cloud provider roles. And over time, they did so. And so that meant that it made it harder to reason about which applications could access which cloud provider objects. And they required a fair amount of manual work and configuration by the engineers. Sometimes they would have to put an annotation on a Kubernetes thing. Sometimes they would have to create credentials, store them in Vault to retrieve later. Sometimes they would have to update Vault access with, a PR into the repo that has Vault configuration. Always some sort of work there. And none of those details really were key to what the application developers were doing. They just had to worry about it because of implementation. We wanted to be able to take care of that at the platform level for our engineers. And so Ian can tell us a little bit about how we started with that.
Yeah, so as Tabitha mentioned, we use HashiCorp Vault across many of our systems for initially very heavily focused on static credential storage and internal PKI usage. But over time, we've expanded and use it heavily for ephemeral cloud provider credentials, TLS certificates, OIDC WTs, and more. One of the things we saw was that just over time, we kept finding that we found that asking engineers to write and manage Vault access policies for themselves or their applications was a source of engineering frustration, misconfiguration, and challenges. And so like to the point of, and then it started to sort of take on an extra layer of absurdity where users would sort of try to figure out what policy they needed to write in this policy language they weren't familiar with, didn't work with day to day, would write a policy, and then a reviewer from a team more familiar with it and responsible for it would review it and say, no, sorry, this is actually the policy you wanted to write. And what we found through that was that we had all the information we needed to write the correct policy. Not only did we have that information as operators, but we had that information from the environment based on the service name, things like that. And that started to, I think, tilt us towards thinking about every time that we asked a user to do a manual security related configuration, that was really telling us we had a gap in our internal product, in our internal platforms. And that was a requirement for us to figure out how do we not just make, less work for the human, but take the humans out of the loop. And one of the first places we really started to apply this methodology idea was around those Vault policies, where we started to take the Vault policies. So I've got a snippet here that's from one of the common policies we use for most or all of our Kubernetes services. It's written in the Vault HCL, I guess HashiCorp, their HCL language, but it's Vault's ACL policy language. And what you'll see in here is a bunch of curly brace sort of templating looking things that say identity, entity, metadata, namespace. That is a sort of unfortunately verbose way of pulling in attributes from things about the identity in Vault, like its namespace or service account in the case of Kubernetes, so that we can automatically entitle those applications to read from specific paths based on their identity. So in this case, we're looking at 4 particular ACLs. The top 2 are related to letting Azure tokens and lets an application get access to eligible Azure subscriptions, but only for their namespace and service account. They aren't able to access other namespace and service account-based roles that we've configured, and they don't have to set up the roles, they don't have to set up the policies, it's just they get it automatically based on that namespace and service account. Bottom half is a similar idea, but with PKI or for TLS certificates. And so on the back end, we've got these policies. We operate the Kubernetes clusters. We have a very good idea of what namespaces and service accounts are operating in our environment and should be operating. And we watch and consume those automatically and pre-configure these roles. So for instance, maybe on the PKI ones for TLS certificates, if we see something in let's keep using the Rocky namespace and service account Bullwinkle that I used earlier, if we see that come in, we're able to configure a Vault PKI backend role that says you can get TLS certificates for these internal domains that are tied to that namespace. And we just configure that automatically using controllers. If applications don't use it, the cost to us to configure it's 0. It's all automated. We just run from a list of known service accounts. But if they do want to use it, the cost of the user is 0. So we basically pre-configure this for everything, whether applications are actively using it or not. So yeah, this is sort of to walk through that example again just a little bit. Different namespace. Frostbite Falls, Bullwinkle, but similar idea. Those get taken together. They get formed into that templated Vault, in this case, AWS account path. We've got an account number in there. This lets us sort of structure out in a very standard way. We know that all the things in our vaults under Cloud AWS are cloud provider secrets backends. We organize them by account number. This makes it easy for us to delegate or manage access to it. Vault has a pretty implied hierarchical policy structure. So this lets us sort of structure it by account, as well as being very clear when we look at like audit logs and things like that, what we're looking at. And then Frostbite Falls, Bullwinkle. And And then under the hood, we're going to map that to an AWS IAM role that is dd.frostbitefalls_Bullwinkle. It's sort of arbitrary how we map it. We could be mapping each namespace and service account to an IAM role that's just a randomly generated string. We found it was really valuable to be able to see in CloudTrail logs and things human-friendly identifiers. But different cloud providers and different systems have different naming rules. And we wanted to make sure that our auto-generated roles wouldn't collide with other existing legacy roles or other future use cases. So that's why you see maybe that DD dot that we use doesn't take up a lot of our key space, but helps us segment it, as well as things like the camel casing and things for providers that maybe don't support dashes in the name. Lets us avoid collisions between different service accounts and namespaces while keeping something that's pretty human-friendly and programmatic. So what we found was by automating both initially the policy part, that sort of templated policy, initially we were able to say you get free KV storage in Vault for your namespace and your service account and nothing else can read it. Here's kind of a cubby hole for you. And then we sort of ticked over into the, well, maybe we can do this for TLS certificates, like I mentioned. And then the last piece, we're like, wait, why even, we can use these dynamic backends in Vault for AWS and GCP and Azure and other cloud providers. Can we, combine that previous idea and start doing it? And what we found that this was great for usability and security and reliability. It moved the brokering of starting to use these dynamic backends, moved the brokering of exchanging a Kubernetes service account for a cloud provider IAM role out of those nodes and out of individual places and into a highly trusted system that, almost more importantly than the trust, we had high centralized visibility into. We can go into Vault audit logs and we can see this application, this pod got these IAM credentials at this point, which for both incidents and reliability focused things, but also security investigations is worth an immense amount. One thing I think we've learned through rolling out a lot of this is stopping bad things from happening is critical for security. But just the same as reliability, stopping reliability incidents from happening is very important, but being able to respond incredibly quickly and effectively to incidents when they do happen, because they do and they will happen, is just as important. And so like this moves that brokering to a place where we can operate it more effectively and safely. That consistent one-to-one mapping of Kubernetes service accounts to cloud provider roles helped us simulate incident management. I no longer have to say, oh, you have this role name that's, says foobar. I don't know what services are tied to that. Let me try to backtrace like what Kubernetes services are using that. We can see it in logs and say like, look, it says Frostbite Falls Bullwinkle. We know based on the rest of facts in our system, we can intuit that that is tied to the Frostbite Falls namespace and the Bullwinkle service account, which is just worth its weight in gold for us. And we can similarly assert that each IAM role for Kubernetes things is used by one and only one service account in Kubernetes, which just takes a lot of ambiguity out of things when we're trying to troubleshoot or make decisions about, do we need to remove access or permissions from this to respond effectively to this issue we've seen. And then lastly, auto-configuring the roles and using these default templated policies, it cut down on the configuration engineers need to do just to get a new service or to improve an existing service to help our customers and improve our product. But I've left out a huge part of all this. I talked about how we configure a system to issue credentials automatically, but that's really not enough. That's not the whole thing. It's very important that we enable applications to consume it easily. And that's where a system that we call Emissary steps in. Emissary is a zero configuration injected sidecar container that provides access enablement services and emulates cloud provider instance metadata services, or IMDS, APIs. So unpacking that a little bit, it's a sidecar. This is a container within a pod that applications can generally expect to be present and running at all times during the application lifecycle. This is now supported in Kubernetes starting in version 1.28 natively. Previously, we had some custom patches to enable this. It's injected. Our users don't have to copy paste container specs into their charts that then we have to ask them to update or change as we update Emissary. We have an admission controller, and if we see a single injection that just has our domain namespace and then Emissary and an inject directive on it, we inject the entire container spec. When we update new versions, we can update what we're injecting, and so new pods get readmitted and get the updated sidecars injected into it. It's non-configurable. Engineers really don't tend to look at their pod specs when they start troubleshooting a reliability or security incident. They're sort of going based on their past experiences, the intuition they built up by interacting with the environment around them. And so I think one of the things we found with kubedym and other approaches was a user would maybe page us in for help and say, my AWS access is broken, my GCP access is broken, can you help me? And we'd say, well, what service account are you, or like what role are you using in IAM to access it? And they say, I don't know. Because they don't. They set it up once, or someone on their team set it up 2 years ago, and everything's just worked fine for 2 years. And it's not a detail that's relevant or critical or important to them that they'd even be aware of. And so taking out that sort of configuration so that we can get right into the incident, or if it's even not an incident, maybe we're just helping somebody develop a new feature, we can just go in and say, here's the answer. Like, it's going to be this. And we take these sort of low leverage, like low impact conversations about like, well, what role should I use, or what should I do for this new thing I'm doing? It's just answered. It's sort of a consequence of the system. We found that to be tremendously valuable. In the sense that I think sometimes I end up telling people internally that like configuration in this context for users is not helpful. It's actually a burden. It's a tax. We're asking them to understand more details about internals that we can probably make the right choice for them. So under the hood, we've injected a sidecar. It has some listeners on it that only listen on the local host within the pod, within the pod's network. An emissary uses the pod's Kubernetes service account token that Kubernetes provides as one of its core features to log into those Vault clusters I mentioned before, and then exchange its Vault token that is logged in with using its identity for the cloud provider credentials from the AWS secrets backends I talked about in the previous slides. One of the really nice features of this is because emissary is just another container in the pod and has zero special access or entitlements on its own, we get identity-based security boundaries out of the box. Emissary isn't a separate service we have to reason about or think about as trust boundary. Emissary is just a helpful client that can do anything the pod can do and can't do anything the pod can't do. So we take this sort of extra layer of reasoning about like broker permissions, like it exists, right? We're still using Vault and things, but for the end user experience, that last mile delivery is just the pod acting as itself, and we don't have an extra layer to reason about there. Cool. So what does this look like a little bit more in detail and a little more in practice? We will be asking people if they memorize the diagram at the end during Q&A. I'm kidding. But let's walk through this just a little bit. So calling Vault requires logging in and managing the renewal of a Vault token in the background. This is another thing that it's a little bit bug prone and tricky to get right. You've got asynchronous code keeping a time-bound token that's constantly threatening to expire up to date. And it's sort of, it's low value if every team has to rewrite its own version of like renewing a token. Like I've written, plenty of things like this, and it's sort of fun to a point, but like I want our engineers to be able to, work on the things that make our product better and not sort of renewal code that's going to look the same for every single one of our applications. So we internalize that. And so we internalize it further than just the cloud provider credentials, and we actually use under the hood. It's now built around the open source Vault agent. We initially did a lot of this work prior to that being open source, and so wrote our own proxy initially. But how that works is very similar to the cloud provider IMDS services, where Vault clients are configured to always follow a Vault adder invar. And when we inject the emissary container, we inject that the Vault adder is this local host address and it's a specific port. So all the Vault clients for users don't need to know where's the Vault cluster I talk to or how do I log in. They just make a new Vault client. Like if you're using the Go SDK, it is Vault package.new client with the default config. One line, you get the Vault client, and then you do Vault also the Golang one .read. .logical.read. Apologies if I got any details wrong on that. And you put in your path, and it just works because it goes through. It's intercepted by emissary acting effectively as a proxy. It's not even intercepted. Your pod is just, your container has been told, go just talk to this local host if you need things from Vault. That gets sent to emissary. Emissary gets it, attaches the Vault token that it's been managing and stewarding and taking care of, and dispatches it to the right Vault cluster, where Vault gets the request and responds with the secret. Cool. So this was really good, but we still haven't gotten to cloud provider credentials. We've talked about automating delivery of KV Vault secrets. There were some interesting things there about doing it without configuring the client, which was great. There's a lot about very good things about that approach, but we still aren't at the point where a user can just make a new AWS client using Bodo and Python or whichever SDKs and just start talking to S3, where they're not managing credentials, they're not having to figure any of that out. And so we put a lot of those things together into something that we initially kind of called Pod Native Cloud Access, but now just sort of think of it as part of Emissary. And it's built around APIs that the cloud providers have. Many of you are likely familiar with the cloud provider Instance Metadata Services and other similarly named things. I'm using, I think AWS most directly uses that name, but Azure, Google, Oracle, other cloud providers all have variations on this idea. And how it works is when you make a new, just to use a couple AWS examples, when you make a new EC2 virtual machine, you give it an instance profile, and AWS spins up the virtual machine, and they control the virtual machine, and they attach a listener to it. And that listener listens on a linked local address that's only accessible by things in that network space. And that server, when you ask it for credentials, will say, yeah, you're running on the same host. I know this host has the instance profile. What do we use here today? Jimmy Smith. So let me give you AWS STS credentials for Jimmy Smith. And these are just pretty simple HTTP APIs. AWS a couple years ago added IMDS v2, which adds one extra sort of handshaking sort of interchange. But they're fundamentally just pretty simple HTTP APIs. I don't know, Tabitha, if you want me to hand off to you here.
Yeah, sure.
Okay,
Yeah, and so with that kind of experience now built into our Vault clients with Emissary and the auto injection in Kubernetes, it is this natural question of, can we do the same sort of thing to broker cloud provider access? And the answer is yes, but it takes work. Slide. So if you take the diagrams from the previous diagram slides and set them next to each other and squeeze until there's one diagram, you get something like this, where instead of having the application that's running on a Kubernetes node or whatever talk to the genuine cloud provider instance metadata store, it can talk instead to one that we have created and that we display inside the pod through the use of Kubernetes tricks when we inject that sidecar. And so if you have that code running there in that sidecar, then you can go ahead and emulate that, go back and talk to Vault in order to get the genuine credentials so that the code that's running on the node in the pod right next to the application isn't doing any of the really sensitive stuff. It's just basically shuffling data around in a way that looks like what the cloud provider API would be doing. And if you click slides twice, then you get it like this. You have your application that's running inside the container. It pulls the appropriate configuration from environment variables, whatever, and talks to Emissary. Emissary has a thin layer inside that understands and emulates a couple of cloud provider APIs and doesn't do the hard stuff. It then defers to Vault to do the hard stuff, where Vault then looks at the credentials that Emissary provides from Kubernetes, verifies that that Emissary really is the particular pod in the particular namespace that it says it is, because it has trustworthy credentials from the Kubernetes API server. And then Vault uses its own access to the AWS API in order to get credentials that correspond to that namespace and passes them back through to the application code in the container. Then the application code in the container goes and talks to the cloud provider, and it doesn't need to know or care anymore whether it's actually really running on that cloud provider or not, whether it's actually really running in that cloud account or not. It talks to something that looks and smells and walks and talks just like the native cloud provider metadata API, and so therefore it's good enough to be that. And this means that application developers can use the normal cloud provider SDKs in their standard way, and they work without even needing to know whether they're really there or not. So now you can handle the cross account use cases or the inter project use cases, and they look just the same as the native use cases where you're talking to the cloud provider you're actually running on. And slide, just like this was good for security, reliability, and usability when it was KV store access for secrets in Vault, it turns out that it has been really good for all three of these things in the cloud provider access case as well. It all just looks and works identically to what the documentation from the cloud providers examples would expect, regardless of where it's running. And so that means that there is a lot less for application developers to have to worry about, which means there is a lot less for them to potentially get wrong or have diverging implementations of. And that means that a lot of either security or reliability bugs that come from subtle implementation differences just can't happen because there's only one implementation. It's the implementation that we have baked into the platform. This also lets the application developers use and trust the SDKs provided by the cloud providers that they are accessing. So, a lot of the basic cloud provider APIs are simple enough HTTP requests, and you can roll your own client for S3 fairly easily, but emphasis on fairly there. Like, it's easy to make something that works most of the time. There are scary back corners in each cloud provider API. And so making something that always works right all of the time is not as simple as making something that mostly works most of the time. So again, engineers can use the SDKs provided by the cloud providers in the way that they are intended to be used, even when the circumstances are not the original circumstances that the cloud provider expected. So now this approach means that Kubernetes pods can safely and transparently access resources within cloud providers and cloud accounts in a way that's completely separate from what cloud provider or account they're running in, and is instead based on the bits of policy that are explicitly configured in places. So if there is a Kubernetes namespace called Frostbite Falls, in which application developers run a certain application, if that application needs to save something into a GCP bucket, they can make their configuration for Google Cloud permissions in the appropriate account, talking about Frostbite Falls, and they don't have to worry about how those interconnections get made. So it means that you have a lot less configuration sprawl, but instead you can look directly in the obvious place where you would expect to look and find the permissions there, and those are the permissions that matter. So all of this simplicity that we can offer to our developers has these reliability and security improvements because it makes reality more readily match their expectation of reality. So, slide. Earlier this year, we open sourced a subset of those IMDS emulation features that we use in Emissary into a project called Attaché. You can find it at github.com/datadog/attaché. And we hope that it can provide some inspiration to help you with your own multi-cloud access challenges. Do you want to add anything there, Ian?
No, not at this point.
Well, then we'll say thank you very much for coming and hanging out with us and chatting about cloud provider access.
Thanks a lot. Thanks, Ian and Tarifa. This is super interesting. So if I sum up a little bit the flow, if I'm a developer using so Emissary, which is the internal version of that, or Attaché, which is the open source version that you published. So I'm going to run my pod. Your admission controller is going to inject Emissary, the Emissary init container and sidecar into my pod. And then what happens is that when my application is going to use like the AWS SDK or the AWS CLI to try to do maybe an AWS S3 CP, it's going to talk to the Instance Metadata Service, which in that case is going to be Emissary. Emissary is going to emulate the same format so that the AWS SDK supports that. And then it's going to talk to Vault. So it's going to say, hey, Vault, here is the service account token from the pod, which it can access because it's running within the same trust boundary. I want credentials for this specific path. Vault is going to know, oh, this path is supposed to give back some dynamic credentials for this specific AWS role. So it's going to assume the role. And in the end, the application gets this credential without having to care about how this is done. Is that kind of the gist of it?
Yep.
Great. So we have a few questions. The first one, which is a great question, I love it, is self-service permissions are great, but how do you make sure that teams are not asking for too much permissions in terms of AWS, Azure, or GCP permissions, right? If you self-serve the permissions, what guardrails do you have in mind, essentially?
So we don't necessarily self-serve all of the permissions. I think one of the major goals of a lot of these systems was to decouple technical enablement of all possibilities and all possible routings and ways we might configure things from these underlying like business risk and policy management. So Emissary and all of that is very focused on the plumbing of like you have a role, a service account, and it's going to be associated with this role. The management of what permissions that role has, we don't automatically grant all permissions to all roles. The specific addition of permissions and attaching them to one of those roles that it's tied to a service account, it still involves human review, depending on the accounts. In some cases, we're able to delegate more things. Certainly, if you start to embrace features like AWS organization management and use smaller scoped accounts, you're able to delegate more things without needing more central review. We also have some things that do require more centralized review for a variety of reasons where an application user will say, hey, my application needs to start reading this bucket. I'm attaching this policy to that role that I already use. Is that okay? And we review it, and usually it includes some business context of I'm doing this feature, and things like that give us enough business context to say, yeah, this makes sense. But the nice thing there is the conversation is never about, oh, well, that role actually can't get that policy because these two pieces of plumbing don't connect there. We don't worry about that. Like the technical plumbing supports the correct business policy judgment, which ultimately lets us spend more time and energy focused on doing the correct business policy and not getting distracted by like technical possibility. So we can focus on making the right choices at the policy and governance points.
Yeah, sort of the glib answer is that's outside the scope of this discussion. But what that means is that you can use whatever kind of change management policy is right for you and use whatever kind of change management tooling is right for you. Perhaps in some workloads, you might just allow users to do whatever they like if it's linked to per user dynamically created sandbox accounts, for example. But in other cases, you might have very strict policy review. And yeah, like Ian was saying, the fact that the plumbing potentially supports anything means that you can not worry about this implementation layer, and you can use whatever sort of permissions management approach you want to use, whatever sort of review approach you want to use. A common example would be to have infrastructure as code that defines the assignments of permissions to those roles, and then use whatever your ordinary code review process would be in order to track the approvals of those requests.
Yeah, and so having one single place where all the IAM stuff goes is really helpful because it allows you to centralize. I mean, you know that nobody is going to create their own policy or role outside of that. So it makes it much easier. Very cool. So there's another question, and feel free to continue asking them. So it's a great one as well. The vault policies that you have shown depend on namespaces and service account names, right? So these become something that you care about. How do you make sure? How do we make sure that users don't create or use namespaces or service accounts that they are not supposed to use, since they are now trust boundaries?
Yeah, so it is a concern we have to take on with this. I think when we look at our systems, I guess taking a step back and looking at like GCP or Azure or AWS, each has their equivalent of Azure subscription or GCP project or an AWS account that over time, I think, looking through best practices and how people tend to manage those, most people seem to converge not on having large monolithic accounts, but having smaller sort of sandboxes or team or product or service scoped accounts or projects.
Tiny bubbles.
And delegating that to people. Because it turns out reviewing small security changes to one large system with many components is, I don't want to say impossible, but pretty close to it. It requires a lot of human context and a lot of human reasoning about thinking about AWS policies and can this change possibly cause something else weird? It's very difficult to reason about. So the same way that on reliability and uptime type things, we split things into smaller blast radiuses. So when you lose one database, you only lose 10% of your uptime or things like that, or 10% of your traffic handling. Like similarly with security, like I think we've seen that evolve pretty naturally as well with having smaller accounts so that like when you do make review mistakes, when you do over permission things, you can say only this service or only this team's products were in that blast radius. So I think it's a similar idea for us and namespaces internally. And I think we came into this approach a bit because our identity model is very agnostic to the underlying clusters. We have an internal concept of a cell that we run multiple clusters in, and we balance services, a single service across multiple of those clusters. And so it's very important for us when we like reload balance or add new clusters into that cell and a service starts running on it, that they don't need all new credentials and they don't have new roles, because logically it's the same to us. We use Kubernetes, the clusters themselves, not as a security boundary, but more as like almost an auto-scaling group. It is just more compute. And so like we had to have the delegation line somewhere, and cluster, which is a pretty natural one. If you just, you start a new project or a new company today and you start running on EKS, like, yeah, give each team its own EKS. Like it's a pretty natural way to do it. It's just not the road we happen to go down. So like once we started down that path, we needed something to delegate to, and namespace is built into Kubernetes. If you start, I think one of the reasons we got here was before we did a lot of this, we were focused on how do we manage Kubernetes RBAC and like Helm deployments and things like that. And if you're writing Kubernetes, if you're familiar with writing Kubernetes roles and role bindings, writing them segmented smaller than namespace is not impossible, but it's not necessarily an easy to reason about thing. It's the same problem I mentioned with AWS accounts. You have a bunch of fine-grained policies and things with different names constantly changing, and you have to reason about, will this policy cause a problem? And so we opted in that case. Applications get a namespace. That's it. We will give them the namespace. We won't ask questions what happens in it, give or take. And then we'll give the operators of that application access to do whatever in the namespace. We don't have to do fine-grained things. We just say like, you're operating the namespace. You are responsible for everything in it, and we know what permissions it has, so you can have everything within the sandbox. And so by the time we got to doing emissary and the cloud provider things, it was a pretty natural fit. We already had our users conditioned that namespace was a key security boundary and a key building block. So we didn't have to ask our users to understand something new. We were able to keep building on it, and we already had a vested interest in making sure that if Team A was operating that Frostbite Falls namespace, that Team B couldn't accidentally or maliciously deploy into it. So we already sort of had this nascent sort of architecture around that. But just to summarize, like the key thing for us was, how do we build a building block that we can delegate to users and say, this is yours. You have autonomy and agency to operate within this. If it needs to reach out into other things, we'll talk. But within this bubble, it is all yours. So we already had that vested interest and had to make sure that those systems were concerned. But yeah, this model absolutely brings namespace into the key security boundaries.
If I can pull out my soapbox there, namespace is fundamentally the only security boundary in Kubernetes. Like permissions boundary for users. And so I personally very highly recommend that everyone manage namespaces that way. There are various sorts of clever applications that let you delegate to teams the ability to create namespaces. And historically, those sorts of applications have been fonts of unlimited numbers of privilege escalation vulnerabilities. Because within Kubernetes, really the one crisp, trustworthy boundary is namespace. And so the ability to create a namespace in a Kubernetes cluster is, in a lot of ways, the most privileged ability you can have. And so if you wanted to decide within your, organization that your privilege boundary was going to be within the Kubernetes cluster, that's a choice you could make and like create clusters per team or whatever. But if you make that decision, then you would need to do different things, and you would need to have your attaché-like thing hang its permission delegations on what cluster is it coming from. Whereas we have said we are going to centrally manage the existence of Kubernetes clusters. And within those clusters, that means that we have to closely control the creation of namespaces, because namespaces are the place where we delegate permissions at. And I actually encourage that model for everyone, because in the you delegate an entire cluster model, then you end up with some weird mixing of permissions, like when a team needs to run a daemon set on another team's cluster, like say for security hardening daemon set or for observability or whatever, that starts to get awkward. Whereas if you put your permission delegation on the namespace boundary, then that is a little more clear.
Great. So sounds like the answer is basically it's easier to delegate that at a namespace level than at a pod or at a cluster level. And it's also a bit of a paradox, right? Because namespaces are a security boundary in the sense that they allow you to separate the identities in logical chunks, but they're not security boundary in the sense that if you have two pods in two different namespaces, by default they're able to talk to each other, right? So that's interesting.
Yeah. Namespace is a permissions boundary, but not necessarily a security boundary. It's as much of a security boundary as the choices that you make enable it to be.
Perfect. There's one question, and I think we can take one more after that one, which I can take. It's how we talked about STS tokens from Vault. How are these tokens generated? So you'll have to keep me honest on that, but in Vault you have basically authentication backends, which are how you authenticate to Vault, and then dynamic secret backends, which are once you are authenticated, what does it give you back? And what we discussed here was talking about the AWS dynamic secret backend, which is basically a way to configure Vault, where you tell it, hey, use this IAM role or this IAM user to authenticate as Vault to AWS. And then you can configure individually secret backends that can be mounted on different paths to say, when someone reads that path, give them back STS credentials for this specific role, which means that if I read that path, magically Vault is going to authenticate to AWS, do a STS assume role, make sure that the credentials are fresh, and give you back these credentials. Is that a fair assessment, Jan and Tabitha?
Nailed it. And I shared the docs for the generate credentials and put on the
share them
secrets
again.
backend in the
You only
Zoom.
shared them to us.
Oh,
Brilliant. I'm going to paste that in the response as well. And I have a last question from me, actually. So we mentioned that from within the application container, if I try to reach the AWS metadata service, this is going to go through the emissary container. How does that work? Is it like by convention? So environment variable that gets injected? Is it some kind of IP table rules that get created on the node by some kind of init container?
We are using the initial way we rolled this out, we used the net admin capability, cap net admin, to directly bind to and listen to requests to 169.254.169.254. It's sort of a magic IP address or a magic constant. If you look through the cloud provider SDKs, it will just be in there. And in their order of precedence, if they don't see anything telling them otherwise, they haven't been given static keys, they'll look there. So initially, that's what we did. We never loved having cap net admin on everything. And so we talked about various things with IP tables. We talked about using, we use Cilium heavily and talked about, can we like do some interesting things with Cilium so that we don't have to have the elevated permissions, but can still intercept these calls. While we were doing that and other things, the cloud providers, I think I'm speculating a bit here, but I think ran into basically the same problem. And that problem is you want to put IMDS on pod networks basically. And so what you start to see is as AWS Elastic EKS, AKS on Azure, GKS on Google, the hosted Kubernetes solutions come up. You start to see in all the SDKs these different IMBARs creep in that are basically hints saying, hey, look, if you're looking for an IMDS service, it's not 169.254.169.254, it's over here. And so what we've done is adopted the same thing. We've had a few challenges around that. There are certain SDKs that have interesting handling around like trailing slashes and like just weird corner behaviors. But so yeah, TLDR, initially we used capnet admin to basically get the elevated permission to be able to bind on it. That was a trade-off we accepted for rollout because the other advantages were good enough. And before we had to invent something of our own, cloud providers, I think, hit the same issue. And now we're building similarly to the rest of it. Why make our own when we can use sort of de facto adopted standards, even though they're undocumented standards in the sense that cloud providers just sort of put the IMBARs out there and don't always advertise them heavily.
But they at least promise to maintain their SDKs. Like, I'm sure everyone who has worked with cloud provider SDKs has, certain historical complaints about them. But at the very least, you can go and say, hey, we ran into this bug with your SDK, please fix it.
Great. Sounds like a perfect way to wrap things up. We're almost at the top of the hour. So thanks everyone for joining. Thank you, Ian. Thank you, Tabitha. This will be recorded and uploaded on the datadoghq.com website. So stay tuned, and we have some upcoming episodes as well. So if you want to see what's up, we have a bunch of also former episodes. I will just drop that link in the chat. We have various things from databases to security to very different things. So have a look, and thanks a lot for joining, and have a nice day, nice evening, or nice morning, wherever you are.
Thanks a lot for coming, everybody.